Welcome back, focus learners, to today's explainer. You know, sometimes a wall of math numbers looks, well, intimidating, kind of like a foreign language. But today, we're going to transform that wall into a highly logical, completely crackable code. If you've ever stared at a mathematical sequence and felt completely lost, you are in exactly the right place. We are literally building your ultimate code breakers toolkit step by step.
So, first things first, I want you to completely change your perspective for a minute. Toss out the idea of just being a student memorizing math formulas. Instead, I want you to step into the shoes of a master detective. Think of a sequence of numbers as like a crime scene of data. Your job isn't just to look at it. Your job is to spot the hidden rules and find the missing clues. Ready for that?
Okay, let's dive into our roadmap. We're starting with cracking the number pattern, then moving to the missing sequence pieces, upgrading to the nth term, decoding linear sequences, tackling nonlinear sequences, and finally, we'll wrap up with the ultimate codebreaker summary.
Section 1. Cracking the number pattern. Let's grab our first set of basic tools.
Think about visualizing these jumps. It really captures exactly what we're hunting for. In the first example, moving from 1 to 4, then 4 to 7, we're literally jumping forward. We're adding 3 each time. In the next one, we're jumping backward, subtracting 7. And in that last example, man, those numbers are just plummeting. We jump from 1,000,000 all the way down to 100,000 just by dividing by 10. These jumps visually map out the secret heartbeat of the numbers.
Now let's just ground ourselves with some clear terminology so we're all speaking the exact same mathematical language. When we have a number pattern, like the ones we just saw, that's formally called a sequence. And that specific rule we use to jump from one number to the very next one, whether it's adding 3 or dividing by 10, we call that the term-to-term rule. It's your most basic key for unlocking the pattern.
Moving on to Section 2, the missing sequence pieces. Let's put those basic rules to work.
Now, what's really interesting here is how we use that term-to-term rule to kind of play with time, mathematically speaking. Take that third example. We know the rule is add 4, right? So we can easily fill the later empty box just by adding 4 to 15 to get 19. Boom, done. But to find that first missing box, we actually have to reverse our operation. We start at 15 and subtract 4 to go backwards, which gives us 11. Reversing operations is an absolutely vital code-breaking tactic when you need to fill in gaps in your intel.
All right, Section 3. Upgrading to the nth term. This is where things get really good.
Think about this for a second. A term-to-term rule is great for finding the very next number, but what if I asked you to find the 1,000,000th number in that sequence? You'd have to sit there adding 3 1,000,000 times. No way. That's just pure tedium. And that is exactly why we are upgrading to the nth term formula. It's not just some boring equation, it is literally a massive, time-saving superpower. It lets you instantly target and calculate any number in the sequence without needing to know the number that came right before it. A total game changer.
But to build this superpower, we do need to clarify some new algebraic notation. It's simple though. When you see a lowercase n, it simply stands for the position number of the term. So the first term, second term, 50th term, whatever. And when you see UN or TN, that represents the actual value of the sequence at that specific n position. Make sense? With this language unlocked, we are fully prepared to start building actual formulas.
Which brings us to Section 4, decoding linear sequences. Time to crack our first major vault.
Let's walk through this example right here. The sequence is 20, 17, 14, 11. Do you see it? The terms are dropping by a constant difference of 3 every single time. That constant difference is exactly what makes it a linear sequence. And check out that note comparing the linear formula, Tn equals an plus b, to the equation of a straight line on a graph, y equals mx plus c. Actually, scratch that, it's not just a comparison. It means linear sequences literally grow or shrink in a perfectly straight line. So the crucial point here is this highly logical 3-step process for building your linear formula. First, you just find that constant difference. We'll call it a. Second, you write down an. So if your sequence jumps by 2 every time, you just write 2n. Simple. Finally, you look at your actual first term and figure out the adjustment, that's our b, needed to make your an formula match reality when n equals 1. Honestly, it's incredibly satisfying once you practice it a few times.
All right, Section 5. Tackling non-linear sequences. Fair warning, the codes are about to escalate in difficulty. Just look at how rapidly these nonlinear sequences explode in value compared to our simple linear ones. While a linear sequence simply marches upwards step by step, quadratic sequences grow by squaring the number. Cubics?
They multiply it by itself 3 times. And exponential sequences, like 3 to the power of n, they absolutely skyrocket. Because of this, we can no longer rely on a simple constant difference to crack them. We need a bigger toolkit. Let's move to this next example and see how this builds. We have a kind of strange sequence, -1, 6, 25, 62, 123. The trick here is comparison. If you line this sequence up directly beneath a sequence of pure cube numbers, 1, 8, 27, 64, a pattern instantly emerges. Every single term in our mystery sequence is exactly 2 smaller than the pure cube sequence. Therefore, the formula is simply n cubed minus 2. See? We crack complex patterns by finding their relationship to known templates.
And this brilliantly illustrates what we have to do when a simple comparison just isn't enough. For a stubborn quadratic sequence, we use the general quadratic formula. Tn equals an squared plus bn plus c. By plugging in the actual values for the first, second, and third terms, we basically create 3 distinct equations. From there, we do the heavy algebraic lifting, solving simultaneous equations, to isolate and find our secret variables, a, b, and c.
Let's pace ourselves and break that complex algebraic method down into an easily digestible checklist. Step 1. Write down the general quadratic formula. Step 2. Substitute n equals 1, then n equals 2, then n equals 3 to build a system of equations based on your specific sequence. Step 3. Solve those simultaneous equations to find a, b, and c. Oh, and always remember the golden rule of code breaking. Once you have your final formula, substitute n back into it to check your answer and prove you've actually cracked the code correctly.
Finally, Section 6, the ultimate codebreaker summary. Let's bring it all together.
Okay, here are your absolute critical takeaways from today's explainer. First, remember that linear sequences are identified by increasing or decreasing by fixed constant values. Second, nonlinear sequences, like our quadratics, require you to use general formulas, like an squared plus bn plus c, and they often involve solving simultaneous equations. And finally, your ultimate safety net. Always check your final formula by substituting a value for n to ensure it perfectly generates the actual terms in the sequence.
To end today's explainer, I want you to look at this visual sequence. We have diagrams growing in size, literally made of physical squares, dots, and lines. Mathematical formulas aren't just for abstract lists of numbers, you guys. They are the secret language describing the structural growth of the physical world all around us. So, looking at how those squares and lines expand diagram by diagram, can you apply your brand new code-breaking superpower to find the nth term formula for their growth? I'm going to leave you to test your new skills on that one. Keep analyzing, keep calculating, and I will see you in the next explainer.